Now we're going to establish some basic theorems regarding properties of continuous functions. And these results will mainly follow from similar results for just limits of sequences. So let's state the following theorem. Suppose that f and g are continuous on some, not on, at some x. X0 in R. Then the following functions are going to be continuous at x0. A, if we take k times f, it is going to be continuous at x0. B, f plus g is going to be continuous at 0. C, f times g is going to be continuous at 0. D, f over g is continuous at 0, at x0. E, if we take absolute value of f, that function is continuous at x0, and f maximum of f g and minimum of fg are both continuous at x0. So let's try to prove this. And the proof should be fairly straightforward. So let's look at A. If f is continuous at x0, then given any sequence xn such that xn converges to x0, it will follow that the limit as n goes to infinity of f of xn is going to be equal to f of x0, right? That's a consequence of the definition of continuity of a function. So this is f of x0. So now let's consider the limit n goes to infinity of kf of xn. And so what is it? What is the function kf? it's k times the function f. So the values are going to be, we're going to take a limit as n goes to infinity of k times f of xn. Then by properties of limits of sequences, from this we conclude that we can take the constant out. So this should be the same thing as k times the limit n goes to infinity of f of xn. And we know that this limit is equal to f of x0, so we get k times f of x0. Of course, that is the same thing as a function kf evaluated at x0. And so that means that the function kf is continuous at xn by the definition of continuity. So kf is continuous at the point xn, at the point x0, by the sequential definition of continuity. Okay, and that takes care of a part A. Part B is going to be similar. B was f plus g. So if f is continuous at x0, then once again, for any sequence xn such that the limit n goes to infinity of xn is equal to x0, we have that the limit as n goes to infinity of f of xn is f of x0 just as above. Same thing about g. So we can just copy the statement and rephrase it for g. So limit of g of xn is equal to g of x0. And therefore, if we now look at the limit as n goes to infinity of f plus g along the same arbitrary sequence xn, then again we recall what the function f plus g is. F plus g has values equal to the sum of f of x and g of x. So this is the same thing as a limit n approaches infinity, f of xn plus g of xn. Once again, properties of limits of sequences tell me if I have at the limit of a sum of two sequences. This is the same thing as the sum of two limits. So this is equal to the limit n goes to infinity of f of xn plus a limit n goes to infinity of g of xn. And those, of course, are f of x0 and g of x0 respectively. And f of x0 plus g of x0 is actually value of the function f plus g at x0. Right, and so we're done here again. sequential definition of continuity tells us that this means that the function f plus g is continuous at x0. So C where you look at the product f times g is going to be very similar, right? Again, it would be the result is going to be due to the fact that the limit of the product of two sequences is a product of limits. So this is similar. I will leave it up to you to work this out. D. Let's suppose that the same thing is true. Now let me see here. There is one issue that I forgot to mention here. In part D, when we're considering the limit of the ratio, continuity of the ratio, f over g, this is going to be continuous as long as g of x0 is not equal 0. So for D, let's say we have the same data, that f and g are both continuous at x0. Let's copy paste that statement. All right, so then let's suppose also for the function g that g of x0 is not equal to 0. We did prove before that if the limit of a sequence is not equal to 0, then that means that eventually all terms of your sequence are going to be different from 0. Just to remind you about that, so from this and from that, it will follow that g of xn, actually let me write it this way, that there exists a capital N in R such that g of xn is going to be different from 0 if n is bigger than capital N. Now, why is that? Let's try to remember this. So let's say I have a sequence as n goes to infinity, limit of Sn is equal to S0, and S0, let's say, is not equal to 0. What does it mean? By definition of a convergence, definition of a limit, I can find a capital N in R such that if n is bigger than capital N, then Sn minus S0, I can make this less than any number, right, provided that capital N is chosen appropriately. And the number that I'm going to choose here is going to be absolute value of S0 divided by 2. All right, so then this actually is equivalent to saying that for any n bigger than capital N, then Sn minus S0, if I rewrite the same thing without using absolute value sign, that this is less than absolute value of S0 divided by 2, and greater or equal than, not greater or equal, but just greater, than minus absolute value of S0 divided by 2. And so if I divide if I add absolute value, if I just add S0 to all three sides of this inequality, so if n is bigger than capital N, then let's see, S0 minus absolute value of S0 over 2 is less than Sn, which in turn is less than S0 plus absolute value of S0 over 2. And what do we have? We have that if S0 is a positive number, then S0 minus S0 over 2, this quantity, if S0 is positive, is going to be positive, right? Because S0 over 2 is going to be less than S0, and this quantity is going to be even more positive. So Sn is going to be strictly positive. If S0 is less than 0, then this is negative, but this is also negative, right? Because then minus S0 is going to be is going to dominate S0 over 2, so then Sn is negative. And so that means that if S0 is positive, Sn is positive as n is bigger than capital N, and if S0 is negative, then Sn is less than 0 if n is bigger than capital N. Regardless, in both cases, Sn will stay away from 0. Okay. So this is just the reasoning to claim that g of xn is not going to be equal to 0 if n is bigger than capital N, because g of x0, the limit of g of xn is not equal to 0. And if that is true, so therefore, f of xn divided by g of xn is defined for n being bigger than capital N, right? And therefore, if I take a limit of f of xn over g of xn, limit as n goes to infinity, f of xn over g of xn, then this limit is going to be equal to the limit of a top divided by the limit of a bottom, because the fact that g of xn are not equal to 0 and g of x0 is not equal to 0, that is going to satisfy properties of limits, condition of the property of limit that the limit of the ratio is the ratio of two limits. So once again, properties of limits. This means that you get limit n goes to infinity f of xn divided by the limit n goes to infinity g of xn, which gives you f of x0 as a limit of f of xn divided by g of x0. Right, and this is a function f over g evaluated at x0. And of course, one more step that I should add here. This is a limit n goes to infinity of f over g of xn. Right, and so we're done here. Just one minor comment, right? So why is it enough to have this to be true when n is bigger than capital N? When I take a limit, I actually allow the index n, little n, go to infinity. So the constraint that n should be bigger than capital N really is not going to matter here, right? Because what I'm interested in is the behavior of my sequence of numbers when n is large. Okay, so then for basic operations with functions, we see that operating with continuous functions, you end up with a continuous function. So the next thing that we're going to look at is absolute value of f. E. Once again, I'm going to suppose that f is continuous at x0, and so this definition is going to hold. And what I need to do is I need to show that the limit of now, because we're talking about the function absolute value of f, we need to show that the limit of absolute value of f is going to go to absolute value of f of x0. So then if we take a limit as n approaches infinity of absolute value of f at xn, that is of course the same thing as a limit when n goes to infinity of absolute value of f of xn. And we did establish a property before that the limit of the absolute value of the convergent sequence is going to be the limit, is going to be the absolute value of the limit. So again, by the properties of limits that we proved before, we have that this is the same thing as absolute value of limit n goes to infinity of f of xn. And of course, the limit of f of xn, as is indicated in the previous line, is f of x0. So that outcome is the absolute value of f of x0, which in turn is the value of the function absolute value of f at x0. And so again, I verified the sequential definition of continuity, because for an arbitrary sequence xn, I have the limit of absolute value of f at xn is equal to the absolute value of f at x0. Then the statement f. And for the statement f, I'm going to use the following property of maximum and minimum. In fact, I'm going to prove this for maximum only, and you can always provide this another proof for the minimum. Or you can just use the fact that maximum and the minimum are related, right, minus maximum is going, maximum of the minus a function is going to be minus a minimum. So, let me see something first. Okay, so we're going to use the following identity. If I take a maximum of two numbers, a and b, then this can be computed in the following way. You take the average of f plus g, and to that average, you can add 1/2 absolute value of f minus g, or g minus f. It doesn't really matter, right? Because absolute value is the same at plus and minus a number. And you can show this by considering cases. Of different combinations of signs, right? So, in fact, it's not f plus g, sorry, it's a and b. So this is true for any a and b in R. All right, so what do we do now? We do the same thing as before. So I'm going to suppose that f and g are both continuous, which means that all of this stuff is true. And now we're going to see, so I'm not going to suppose anything else here. So by the property, let's label it as star. It is enough to do the following. So we want to verify for the maximum of two functions that for the maximum of two functions, we want to verify that the limit of that maximum evaluated at xn is going to converge to the maximum at x0. So we make the following computation. So I'm going to take a limit n goes to infinity of the max of fg, right? This function evaluated at a point xn. Now what is that? That is a limit as n goes to infinity of a maximum of two values, f of xn, g of xn. And now by the property star, so by star, over here I should be able to write the maximum as a sum of the average and the absolute value. So this would be the same thing as a limit n goes to infinity of 1/2 f of xn plus g of xn plus 1/2 absolute value of f of xn minus g of xn. All right. So we're taking the limit of this entire thing, And now we can use properties of limits again. So this, by properties of limits of sequences, is the same thing as 1/2 limit n goes to infinity f of xn plus 1/2 limit n goes to infinity of g of xn and plus 1/2 limit as n goes to infinity absolute value of f of xn minus g of xn. But we just proved a moment ago that if I take a limit, if I know that f of xn minus g of xn converges to some limit, then limit of absolute value is going to be absolute value of the limit. So what we get then is f of xn we know goes to f of x0, so this limit is f of x0, this limit is g of x0, and this limit is absolute value of f of x0 minus g of x0. So we get 1/2 f of x0 plus 1/2 g of x0 plus 1/2 absolute value of f of x0 minus g of x0. But then I can read the property star backwards, right? What is 1/2 of the average plus 1/2 of the absolute value of difference? That's a maximum. So this would be the same thing as a maximum of f of x0 g of x0. And that, of course, is just a maximum of fg at x0. So again, we verified the sequential definition of a limit, so this function is continuous. One more theorem before we're done with this. So we can combine functions by adding, multiplying, dividing, and so on. And another way in which we can combine functions is that we can look at composite functions. So let's suppose that the function g is continuous at x0. Now, if at the end of the day I'm going to look at the function f of g of x, right, if x is continuous at x0, as I let x approach x0, I'll see g of x0 here. And then I want to evaluate f at g of x0, so as xn goes to x0, g of xn goes to g of x, and g of xn is also a sequence, so then if f is a continuous function, it should be continuous at g of x0, right? Because that's where the sequence g of xn is going to go. So let's write this down here. So if g is continuous at x0 and f is continuous at g of x0, then f composition g is continuous at x0. Why is that true? So once again, if g is continuous at x0, saying that is equivalent to saying that for any sequence xn such that the limit n goes to infinity of xn is equal to x0, it follows that the limit when n goes to infinity of g of xn, this must be g of x0. Right, that's the g to be continuous at x0. Also, f is continuous at g of x0. This is the same thing as saying for any sequence of yn such that the limit n goes to infinity of yn is g of x0, it follows that the limit n goes to infinity of f of yn should be equal to f of g of x0. Right? So just using a definition of continuity of f and g, now f and g are continuous at different points. This is what we get from the sequential definition. So that's part 1 and part 2. So therefore, given a sequence xn such that the limit n goes to infinity of g of xn is equal to g of x0, we have, if I take a limit n goes to infinity of f composition g of my xn, what am I going to get? I'm going to get the limit n goes to infinity. What is f composition g? That's f of g of xn, right? And I'm going to introduce a notation. I'm going to call yn equal to g of xn. Okay? So what do I know? Because limit of g of xn is equal to g of x0, then what I got is a limit n goes to infinity of f of yn, and yn converges to y0 by this limit, right? In fact, let's not even use y0, but it converges to g of x0. Right? So again, I'm calling g of xn yn, and then this says that the limit of yn is g of x0. So yn is a sequence which converges to g of x0. So then because f is continuous at g of x0, then the limit of f of yn must be f of g of x0. And what is f of g of x0? That's the same thing as f composition g of x0. And so what does it mean? It means that the function f composition g is going to be continuous, right? Because for the random sequence xn, decomposition, fg, goes to the composition of fg, f and g at the limiting point x0. So once we gain, this fact is proved. All right, and then that means that now you can use all of these properties to demonstrate continuity of different functions. For example, if you're asked the question, is f of x equal to 1 over x squared plus 1 continuous at x equal to 0? Well, so what do you see here? You see that denominator is a sum of x squared and 1. Assuming that you showed that all polynomial functions are continuous, x squared should be a continuous function anywhere, in particular at 0. So then if I add 1 to x squared, 1 itself is a continuous function. X squared plus 1, sum of two continuous functions. Sorry, we just proved that that sum is continuous. And then x squared plus 1 is always positive. So that means that the limit of a denominator as xn goes to x0, the limit of denominator is going to be non-zero. And then again, 1 is a continuous function. X squared plus 1 is a continuous function. So then the ratio must also be continuous, right? Again, by the properties that we proved. So x squared plus 1 is going to be the first property that we used. So the sum is the property, I think, B. Yes. So by the property B, D, this statement is true, right? That f is a continuous function. All right, next time we're going to introduce even more properties of continuous functions.